Welcome to today's topic. It is a very simple and the last topic of physics, wave optics, and I have chosen Doppler effect in light. So the small topic is very interesting and has a lots of significance and application in day-to-day life. So first of all, let me define what is Doppler effect. So first of all, let us understand what is actually Doppler's effect in light. So Doppler, all of you are quite aware of the Doppler effect of sound, but Doppler effect of light is quite a bit different. So you first of all see the definition: the phenomenon of change of apparent frequency or wavelength of the light due to relative motions of the light source and the observer is called Doppler effect. Means this is the source of light and this source of light is moving, and here this is observer or the target. When it moves, it has velocity, and due to its motion there occurs change in the frequency or wavelength. When it approaches towards it, there occurs the change of frequency of the light. Means when the source of the light moves in between the source of light and the target or the observer, then the frequency of the light or the wavelength changes, either increases or may decreases. When it approaches, it may increase. When it recedes, it may decrease. And due to this change in the frequency or wavelength of the light in between the light source and the target or the observer is called Doppler effect. So there is change in apparent change of frequency. I will explain in a short while. Let us take the example where the source of light is moving towards the observer. This source of light and here observer is fixed, and the source of light is moving towards the fixed observer or target. So now what's happened when the light moves? Let us assume that actual frequency of light source let us assume the actual frequency of the light source which is moving towards the observer or target is nu, and the apparent frequency of the light source is moving towards the observer is nu dash, and actual wavelength is equal to lambda and apparent wavelength is lambda naught. Now what's happened when light, we are taking the example where source of the light moves, the case 1 moves towards the observer. This is the very simple case. When the light source is approaching toward the observer, naturally the frequency is going to be increased. The apparent frequency is going to be increased. That is, apparent frequency is, we have assumed has nu dash is increased. Now the frequency and lambda is inversely proportional. Nu is inversely proportional to lambda. So if the frequency increases on approaching towards the target, then lambda will decrease. So what's happened? So we can write the apparent frequency is equal to nu is equal to root over 1 plus b by c, where b is the apparent velocity of the source approaching towards the target, and 1 by b minus c, and lambda bar is equal to nu equal to root over 1 minus b by c is equal to 1 plus b by c. Since the frequency increases, so the term denominator is in law, that is small, and since lambda is inverse proportion is decreases, means denominator is becoming bigger and bigger, means plus term. Hence, to keep it in your mind, the technique is that when increase, then 1 minus b by c, means this term is in denominator is with small value, and when lambda is increasing, means denominator with bigger value, bigger the value, smaller the value of apparent lambda. So we get this relation when one with apparent frequency, another with apparent wavelength. Apparent frequency increases on moving towards the target, and apparent wavelength decreases on moving towards the target. Now the case when the velocity of the light source which is approaching towards the target is less than the velocity of light. See the velocity of light in 10⁸ meter per second. Then this nu bar, nu dash is equal to nu. Then at this condition, nu dash is equal to nu into 1 plus b by c, and this tends to 1. 1 minus b by c tends to 1 when the velocity is smaller and smaller than velocity of light. Then nu bar is equal to 1 plus v by c. That is, nu means apparent frequency is equal to actual frequency into 1 plus this. So we can write simple by simple calculation, change in frequency is equal to actual frequency into v by c. Or in other words, we can say that is fraction of change in frequency when the light source is moving towards the observer. The change in frequency, that is the frequency of the source, is increasing, apparent frequency is increasing. Then this change, that is actual frequency and apparent frequency, that del nu, this change in frequency is equal to nu into v by c, or the fraction of change in frequency. What fraction is changed when the light source is approaching towards the observer is change in frequency divided by actual frequency is equal to v by c. Then fraction of frequency is equal to v by c. It is a formula, please keep it in your mind. Very simple. Then so from this condition we get lambda dash apparent wavelength is equal to actual wavelength into 1 minus b by c. Then 1 plus b by c tends to 1, is approaching towards 1. So lambda dash at this condition, lambda dash equal to lambda into 1 by c. So where you get lambda dash minus lambda is equal to, so change in lambda is equal to lambda, actual lambda is equal to v by c, or fraction in change of lambda is so as earlier we have got fraction of change in frequency is equal to del frequency by original actual frequency is equal to v by c. Hence here also change in wavelength is equal to change in wavelength by change in fraction of wavelength equal to del lambda by lambda is equal to v by c. Now Doppler shift. So it is the case where the source of light is moving towards the observer. So at this stage we see apparent wavelength is less than actual wavelength of the source of light. Now so Here, when the apparent wavelength is decreasing, when the source of the light is moving towards the observer, then the spectra of the radiation coming out from the source is having wavelength, decreased wavelength. So when wavelength decreases, that is frequency increases. That is, when it was approaching towards the source, the frequency increased, the apparent frequency was increased. With apparent increased frequency, wavelength is less. So if the wavelength is less, so it will red light is the highest wavelength, and in this order wavelength of light decreases, so it is approaching towards the blue. So in this case, the radiation or the spectrum of the radiation of the light emitting out from the source will approach towards blue end of the spectra as the wavelength is decreasing, and that shift is called blue shift. So it is one of the very important thing that when you are asked, when you from this spectra, picture of the spectra, you can find that if the spectra of the approaches towards the blue end, we can tell the source of the light is approaching towards the observer, since the wavelength, apparent wavelength is decreasing. So if apparent wavelength decreasing, it means the source of light is approaching towards the observer. Means from this we can infer or get a lot of information from the shift, whether it is blue shift, other is red shift. Observer, if thus it is observer, if the source of light starts receding from, it is the source of the light receding from the observer or moving away from the observer, naturally it happens, if such thing happens, then apparent frequency will be less than original frequency, actual frequency, because it is receding out, it is receding from the observer. So the frequency will by due degrees will decrease, so frequency will be less, apparent wavelength will be more than actual wavelength. It is inversely proportional. So our earlier expression will be just reverse of the first case. Here, if the apparent frequency of the source is decreasing, means denominator will be moved, so have assumed here plus, denominator plus, and the apparent wavelength is increasing, means yeah, denominator is having less value, 1 minus something less value, it is the reverse of this one. So at the earlier condition, if you assume velocity of the source is less than the light, then at this condition apparent frequency is equal to, so I am not doing it as early, we can get del of nu is equal to nu into v by c, or fraction of nu, change in nu frequency equal to del nu by nu is equal to b by c. So also from this I am jumping the step, we can write del of change in lambda is equal to lambda into b by c, because at the condition b by c is equal to nu naught, apparent frequency equal to this equal to upper part, lower part tends to 1, and so also here nu bar is equal to lambda. At this condition it will be lambda bar is equal to lambda into 1 plus b by c. So from this you will get change in wavelength equal to lambda into this. So fraction in change in wavelength del lambda by lambda is equal to v by c. Now it is second condition, when source of light is moving away from the observer. Now at this condition what's happened, we know lambda bar is equal to 1 plus b by c, where apparent frequency is more than the actual frequency when it is receding out from the source. Now what is Doppler shift? lambda dash is greater than lambda, the frequency is more than the actual frequency. So the frequency order in this way, red is the highest. So if the frequency is increasing, means it is frequency, means wavelength, apparent wavelength is increasing, means wavelength increasing means it is going up, that is coming towards red. If it is decreasing wavelength, increased lambda, lambda if increase going up, it will come to the red. And if the lambda change, lambda dash changes, means it is going downward, means shifting is towards blue. So here Doppler shift will be towards red, shift towards the region of red end, and it is called red shift. So from this we can assume that if a substance or the source of light moves away from the target, then lambda increases, and if lambda increases, the emission spectra or the spectra of the radiation will shift towards right, red, and hence we can infer that if the spectra changes or shift towards red, that indicates an object or substance is will move away from the source. From this we can infer whether star is going away from us or coming towards us from the Doppler shift or the figure or the of spectrum we can tell. So next part is Doppler broadening. So a bit just let me explain what is Doppler broadening. When a gas, when any type of gas is enclosed in a container, so what's happened? The atoms in the gas molecule starts moving randomly in all direction. And if you want to take the spectra of the light emitted from the atoms due to the Doppler effect, means sometimes the atoms of the gas starts moving away from the detector because it is in the discharge state, and some of the gas molecules starts moving towards the detector. That's why there will change in the apparent frequency and change in the apparent wavelength of the light. Due to this, there occurs Doppler effect, and due to this change in the frequency or change in the wavelength of the light emitted coming from the atoms moving in the various direction. So the frequency is not observed as having single value. The frequency, that if you measure the frequency, if you want to measure the frequency, you will get that frequency doesn't have any single value. It will be in a range of values in between this and this, and this is the reason this broadens the spectral lines and amount twice into lambda, and hence this change in lambda due to this not single line, it's a range, and this range broadens the spectral lines becomes broadened. And when this spectral lines broadens by the factor or amount twice change in the lambda, then it is called Doppler broadening. And this depends on the velocity of light, and velocity of depends on the temperature. Hence it depends on the root over t temperature. It depends on velocity of light and temperature. So this is Doppler broadening. The next and last part of this today's topic is radar, and it is very much important in today's modern warfare system. It is a system, one radar, it is a system which is based on the system of locating the distant object by means of the reflection of radio waves, spatially or usually microwave frequency, and it is used for navigation and guidance of aircraft. And radar employs the Doppler effect, where the transmitted frequency and received frequency difference is measured, and out of this difference it is detected or located whether uh, locates whether the source, not target, whether the source is moving or stationary. That is, already we have calculated nu is equal to delta, del of nu is equal to nu into c by v, but here we will give only a term 2 here, and del lambda is equal to lambda into 2 into c by v. 2 is due to reflection, and the factor 2 is due to reflection, and when the value of this value is equal to positive, it means the object is approaching. When the value del lambda, that value is negative, it means the object is receding. Not lambda, you give this value, it means receding. So by obtaining the frequency, apparent frequency and original frequency of the source, and by finding out the value, putting the value here with this, we get the value positive and negative. With the help of this, we can tell that whether the object is coming towards us or the object is receding from us. So this is the main principle of radar. In short, a lot of other things are there also. Thanks a lot for watching the class. In the next class, I will start solving out the entrance exam solution on the chapter. Please don't forget to subscribe the class.